So let us start our lecture today in the course of electronics and electrical circuits for BSc Part 1. It is also useful for BTech first year students and standard 12 students preparing for competitive exams, because the stuff that is provided here, the notes or the content that is provided here, that is in the most detailed form, and I don't think that anybody in the YouTube they provide this much details lectures. I have seen many of them, but it is unfortunate that we don't get views, so we should not bother about the results and start our work. So in the course of in the last lectures that were in Hindi language, we studied about the ripple factor, we studied about the capacitive factor. Now what we learned, that how does a capacitor filter out the ripples, what is the physics behind, and how to calculate the ripple factor of a capacitor filter circuits. There are certain questions that I have taken, and we will see what is the solution of these questions. So let us start. So as I told you in the last lecture, that capacitor, it is basically an inertia factor. It is basically an inertia element. Inertia element means something like mass in mechanics, that opposes any change in a particular quantity. Mass opposes change in the velocity. So what happens here, the working of this capacitor filter is based on two factors. First one is charging and discharging of capacitor. Charging and discharging of capacitor and the next factor is that capacitor is an inertia element. Capacitor is an inertia element. Inertia element that opposes change in current, that opposes change in voltage, change in voltage. You must have studied that the energy stored in a capacitor is half mv square. This can be related to half mv square, it is half cv square, half mv square. These two quantities, they represent inertia. This is mechanical inertia, this is called electrostatic inertia. They do not allow any change to occur in the quantity that is in square. Electrostatic inertia. So these are inertia elements basically, and the functioning of this capacitor, of this filter circuit, is based on these two factors. Okay. So what happens when you have an input AC, when an AC supply, this is the form of AC, sinusoidal varying voltage. AC supply is fed to a circuit of rectifier with a capacitor filter. Then the capacitor, the first process I discussed is the charging and discharging of the capacitor. Then the capacitor charges in the positive half of the input AC. Then the capacitor charges, or you can say stores charge, in the first half of the cycle. Means when the peak is positive peak, this one, during this time charging of capacitor occurs. Charging of capacitor is charging at this time. It is storing energy in the form of electrostatic field. And during the negative half, other half, the capacitor discharges, it releases all its energy. During the negative half, during the negative half, the capacitor discharges. Capacitor discharges means during this period, this is the positive half, this one is the negative half, this is the discharging process, this is the step where the capacitor discharges. So it is non-conducting. So capacitor basically opposes any change that is occurring in the voltage. So when it is connected across a pulsating DC voltage, now try to understand this. Pulsating DC voltage means that voltage is not constant. It has some AC components. There are some components that are changing. So this capacitor opposes all those changing components in the DC, in the output DC. That is why it is that this is the mechanism by which it filters out the AC components. This is something in a crude sense like the shock absorber. When you are moving on a bike and there is a bump or there is a ditch, and when you cross that bump or ditch, you feel some jerk. That is change in energy. The shock absorber is absorbing that energy in compression, and you are relieved of that energy. That you do not feel that change if the shock absorber is very good. So this is occurring here. Since the output of a rectifier is a pulsated DC, this is the form of pulsated DC. There are some changes. These are the changes in voltage. Changes in voltage that we call the ripples or AC components. So these changes are opposed by the capacitor as it is an inertia element. The changes in voltage or the ripples are opposed, and this opposition causes storage of energy. This is the significant aspect of an inertia element. The changes are opposed by the capacitor, and then the capacitor removes the ripples, and there is a smooth output. This is the basic mechanism. This is the basic physics of a capacitor filter. This is how it is used. This is how it is smoothing out the AC components or the changes. It is removing the ripples in the output DC. This is the basic mechanism. Okay. Now, in the course of rectification, in the positive half cycle, the diode is forward biased. In the positive half cycle, positive half of the input AC, the diode is forward biased. This we know, forward biased. And if we are considering that it is an ideal diode, this means it is providing zero resistance. Now try to relate the things. If the resistance R is zero, forward resistance, then the time constant will be zero. This means time constant, which is R into C, it will be zero as R is zero. This means that the capacitor will charge instantly. That the capacitor will charge to the peak value. Of course, capacitor will charge to the peak value peak value instantly without any delay, because time constant is the time required to charge the capacitor to 63%. And this, if this time constant is 0, then the capacitor will charge instantly. It will not take any time. So this is a very interesting situation in the negative. And now the capacitor holds this charge as it is an inertia element. The capacitor holds the charge until the AC input goes negative. Until the AC input goes negative. This charge is stored in the form of energy half CV square. The capacitor discharges through the load. Capacitor discharges through the load. Through the load. Now during negative half cycle, what happens? During negative half, the diode resistance is high. Diode resistance is high. And the time constant is also very high. Time constant is also very high. So what is the effect? Time constant T is equal to RC is very high, as this one is high in the negative bias or in the negative peak when the diode is reverse biased. Now what is the result? The discharging time is about 100 times larger than the charging time. About 100 times larger than the charging time. Diodes are not always ideal diode. They have some forward resistance, so they will have the capacitor charging time. It will have a small value during the positive peak, but in the reverse bias, during the negative peak, the diode resistance is very high and the discharging time is very long compared to the charging time. This is the basic factor, that between two peaks of AC, if this one is the first peak, second one is this one, if this is the time between the two peaks of the AC, the time constant RC, I am writing this as constant RC, is much larger than TAC. So the capacitor is slightly discharged between these two peaks. And this is a fundamental requirement. So the capacitor is only slightly discharged. Slightly discharged between the peaks. This is a very fundamental mechanism. This is a very fundamental action. So the decrease in ripple, it is due to this time constant. Now the diode, now there is a term called the surging current. Surging current. Surge means sudden flow of current. So the output diode current is a surging current. Surging means sudden impulses. Sudden impulses. Surging current. Output voltage is always greater than the capacitor voltage, and this is the voltage that you get across the load. So to remove the surges, a limiting resistor is connected in the practical circuits. Limiting resistor is connected in the practical circuits. In practical circuits, This resistor reduces surging current. The main effect of this limiting resistor is to further smooth out the output DC. The limiting resistor further smooths the output current. So the basic mechanism is the short discharge time, the discharge which is occurring very slowly of the capacitor. It removes the ripple factors. Before the capacitor is totally fully discharged, it is again charged by another pulse of the incident AC or the input AC. And this is how the discontinuity in the output that was observed before applying the capacitor, this is the discontinuous pulsating DC. Discontinuous DC pulsating. Now after filtering by capacitor, this becomes more smoother. These discontinuities are removed and you get a DC. This is the basic mechanism. Now the next question is how to calculate the ripple factor. How to calculate the ripple factor. Let me erase this. How to calculate the ripple factor of a rectifier with capacitor filter. How will you calculate this? We will come to more questions like this. So the calculation is not very difficult. There are certain small assumptions. What we consider is VPP, peak to peak voltage. Voltage is the amount by which the capacitor voltage falls during TR. TR is the ripple time. You can understand this ripple time since the ripple is an AC component. It is the time period of the AC wave. TR is the time period of the AC component, which is the ripple factor, ripple factor. So you can calculate this ripple peak to peak voltage. This is the ripple peak to peak voltage. As so V is Q by C, change is dQ by C. This is a very important concept. Current you can write I DC into T times R. Current is Q by T and this is the TR time. So multiplying by I, you get the charge and C. So this can be written as VDC by FR, the frequency of the ripple, CRL. So that our DC current, the magnitude of DC current is IDC is equal to VDC by RL. This is the calculation we have seen in the last lecture. Now the ripple voltage or the ripple output is assumed to be of triangular form. There are several waveforms that can be obtained, but it is generally assumed to be of triangular waveform. Triangular waveform. So using this assumption, the ripple voltage peak to peak, it can be written as V ripple peak to peak by 2 root 3. This is a factor that comes when you are dealing with AC or triangular waveform. And the RMS value of the ripple voltage is VR peak to peak by 2 root 3 or VDC by 2 root 3 FR CRL. So you can calculate the gamma, the ripple factor, as VRMS by VDC, and it comes out to be 2 root 3 FR CRL. Now one important factor is this: for half wave rectifier, you can comment in the comment section for detailed derivation. I can show that derivation. Because of time constraints, I am using the direct results. For half wave rectifier, this is 2 root 3 FCRL, and for full wave rectifier, this is 1 by 4 root 3 FCRL. So you can see that gamma, the ripple factor for half wave, it is almost 2 times the full wave rectifier. So the full wave rectifier, I am writing in short form, is more efficient. We have seen this in the previous lectures, is more efficient in removing the ripples. You can also use the word minimizing, as ripples are not totally removed. There are some quantities of ripple that are always present. So this is the calculation, this is the calculative part of the capacitive filter. We will address to some more questions, more interesting questions regarding this capacitor filter in the next video, which is scheduled to be published today itself, if everything is alright. So please make your comments, ask your questions. If you have some problems, then you can ask. And the link for in the description box, I have provided the link for the WhatsApp group and the Telegram channel. So you can join if you want to study physics, BSc Part 1, electronics and other papers also. Thank you.